Okay, this is the Chapter 3 notes that we're going to be doing. Oops. Hi. It's the Chapter 3 notes that we're going to be doing. And this is take 3 of the Chapter 3 notes. There goes my cat. And so I can pause for nothing. So this one is going to be the one. Not starting again. So the Chapter 3 notes. So the Chapter 3 talks about system of equations, and what a system of equations is. This is an example of a system of equations. It's got 2 equations in it and 2 unknowns. Also, a system of equations could have 3 equations and 3 unknowns. And the solution to a system of equations is an ordered pair. When you have 2 unknowns, it'll be an ordered pair that makes both equations true. And so it's not good enough to make one of the equations true. You have to make both of the equations true. So this is equation 1. I'm going to label it EQ1 for equation 1. And this is equation 2. I'm going to label it EQ2 for equation 2. And so I want to check, is equation 1 true when x is 0 and y is 27? So we're going to put that in. So 5 times 0 minus 27 for y equals negative 27. And you could put this in your calculator if you wanted to, or you could do it in your head. If you do it in your head or your calculator, either way, you get negative 27 equals negative 27. So that doesn't mean the system is true. That means one of the equations is true. The other equation has to also be true. And so now I got to check on equation 2. And if it's true, then 0, 27 is a solution to the system. If it's not true, then 0, 27 is not a solution to the system. So the other equation is y equals 3 minus x. Y is 27. So 27 equals 3 minus 0. Well, 27 doesn't equal 3. So what this tells us, what the conclusion we can draw from this is nope, right? Is that 0, 27 is not a solution to the system. Has to solve both. So let's try this one. So we got x, y, put it in equation 1 first. So we have 5 times 0 minus 3 equals negative 27. And you can see with your calculator or your head, negative 3 doesn't equal negative 27. There's no reason to even go and check equation 2. It doesn't matter if it solves it or not. So it would 0, 3 would not be a solution to the system. So I'm just going to stop because that's all it was asking me, right? So 0, 3 is not a solution to the system. Must solve both. So now we're looking at negative 4, 7 to see if it is. So equation 1, 5x negative 4 minus 7 equals negative 27. You could use your calculator or your head, and you can see that, well, that's negative 27, right? Negative 20 minus 7 is negative 27. And that does equal negative 27, check. And how about equation 2? So we're going to put the same thing in. So y, right, y is 7, equals 3 minus x, and x is negative 4. So we have a minus of a negative there, subtract of a negative, so it's add. So this is 3 plus 4, which is 7. 7 does equal 7. So this is true. And so what that tells us, since they're both true, it has to solve both. This negative 4, 7 is a solution to the system. Okay, so this was asking us just to check whether or not something was a solution to the system. And now what we are going to do is we're going to find a method of finding the solution to the system. And of course, then we can check it and make sure that it is the solution. They actually talk about in chapter 3, 3 different methods. Kind of funny, 3 different methods in chapter 3. And the first method is the graphing method. And that's good news for us because we did a lot of graphing in chapter 2, so we get to practice our graphing. And so we're going to use the graphing method. It's what it's asking us to do. Solve by the graphing method and then write the solution set. Check your answer. So I'm going to first graph equation 1. Whatever the first one listed is, I call equation 1. So I'm going to graph equation 1. 2x plus y equals -2, and I can graph that any method that I like. It's a line, and I can use convenient points if I like, or I could use solve for y and use the slope and the y-intercept if I like. I could pick the intercepts if I like, whatever I want. Convenient points and picking the intercepts to me is almost the same thing, because the intercepts are when you let 0 be in for x and 0 in for y and solve for the other value. And so those are actually the most convenient points, you know what I mean? And so anything that looks good would be a convenient point. And so if I let x be 0, 2 times 0 is 0, so that tells us y is -2. And if I let y be 0, this works out pretty good because 2x equals -2, right? So x has to be, remember y was 0, -1. And so I can get points pretty good. And now that I've practiced that, I can kind of do it in my head a little bit. It's harder when it's not a 0 to do it in your head. So you can't pick something already in your list. But like I could pick x as 1. It's not already in the list. And so this would be 2 times 1 plus y equals -2. So 2 plus y equals -2. When you solve for y, taking away 2 from both sides, you get y is -4. And so those 3 good points there. So I'm going to plot them: 0, -2, -1, 0, and 1, -4. 2, 3, 4. Okay, so I'm going to graph that line. Now remember that these, all the points on this line, including these 3 points, but all of the infinitely many ordered pairs on this line represent the solutions to this line. Represent the solutions to that equation right there, right? So now I'm going to have equation 2. So this is equation 2. Y equals x plus 4. So probably when I'm picking my convenient points, I'm going to pick 0. When I pick 0, I get 4. I'll probably pick 1. When I pick 1, I get 1 plus 4 is 5. And maybe I'll pick 2. When I pick 2, I get 6. So I'm going to plot those. Over 0, up 4. 1, 2, 3, 4. 1, 5. And 2, 6. And so I'm going to draw this line in here. And every point on this line represents the solutions to this equation right here. So if I want the solution to the system, I'm looking for a point that solves this line and a point that solves this line. In other words, I'm looking for a point that's on both lines, right? And you can see it's right where they cross right here, right? And that certainly looks like the ordered pair -2, 2. Do you guys agree? That's what that looks like. -2, 2. And I want to make sure that I'm right on that and that there is no mistake. So I'm going to come over here and I'm going to just see, is -2, 2 a solution, right? I'm checking this. This is what I'm going to put in and check and see if it solves this. So this would be 2 times -2 plus 2, that's y, equals -2. So that's -4 plus 2 equals -2. So certainly it could have been in this list. So that's good. Could it have been in this list? -2, 2. So if we put it in there, we get y is 2, and we get equals -2 plus 4, and that's certainly true as well. And so this tells me, because it's in both lists and I was checking it, that it is the solution. Sometimes you get a little off on your graphing and then you decide you're not going to check it. You think, it's it. I'm sure it's it. It looks close enough. And it doesn't really solve it. And so I always check it and make sure. And if this did not solve that equation and also solve that equation, then I would plot more points and be a little more accurate on my graphing. And that sometimes happens to me when I'm drawing them, particularly if I don't have a grid paper and a ruler. It happens to me. And they're pretty sweet to you in the book. They always make them cross at whole numbers when they ask you to use the graphing method. And so if they didn't cross at whole numbers, boy, that would be tricky then. And so it'd be a problem. I guess I don't have a lot of light in here. Kind of been in my bat cave all day making videos, and it used to be light outside and now it's gone dark. And so let's see if I turn on some lights here in the bedroom, if that doesn't make it just a tiny bit better. So asking us to solve by the graphing method, and so we're going to do the same here. You get to choose the method that you would like to use for graphing the equations, but I'm going to graph both equations. And see where they intersect one another. So like I could pick x is 0. If x is 0, then y is going to be, see how it's negative y equals 3? So I have to divide by -1, right? So y is -3. So that a negative of a -3 would be a +3. And if x is 0, then, y is 0, then x will be 3. And then you could do anything. 4 take away 1 is 3. So this is 4 and 1, right? I mean, that would be a good way of getting some points. So convenient points are pretty easy to find on this one because it's just not that tricky of a line to graph. So 0, 1, 2, 3. 3, 0, 1, 2, 3. 4, 1. And so they look like they're falling on the same straight line there. And so there's our equation 1. And now I'm going to try to get some points here on equation 2. When I choose x is 0, then I divide both sides here by -2, right? So this is going to be -3. -2 times -3 is 6. When I choose 0 in here for y, right, then I'm going to get 3. 2 times 3 is 6. And that makes me start suspicious. I can't help but notice, can you? So I think, hey, what about 4, 1? Will 4, 1 work? So let's just try it. So 2 times 4 is 8 minus 2. 8 minus 2 is 6. So I became suspicious when I had 2 points that were the same, and just picking my favorite points, the intercepts, right? And so here's me graphing the other. Here, I'll graph it in blue. So here's me graphing line equation 2. I'll graph it in blue. And then you get your ruler out here. And so if you think that it's silly that I'm now graphing it in blue, you're right. It is silly, right? I knew they have the same 3 points. They have the same exact line, right? So I graphed this one in this crazy highlighter blue, and I graphed the other one in pencil. And so remember that the solutions were points that they have, ordered pairs that they have in common. So they don't have just one ordered pair in common. These lines, right, here's the pencil, right, was there, and the blue right on top of it. They're the same line. They have infinitely many points in common. And so your book has a fancy way of writing that. And so they say the set, and so there's their set brackets, of ordered pairs, x comma y, such that, so that's always the same, and I bet you on XYZ it fills that part in for you. And then you just choose either one of these, it doesn't matter, such that x minus y equals 3 equals 3. And that's a way, it's saying that there are infinitely many ordered pairs, but all of the ordered pairs that are a solution to this line. Now I could have picked the other line because they're essentially the same. And a lot of times people will say IMS as just a shortcut of talking about it. And this means infinitely many solutions. It doesn't describe the solution, infinitely many, and there are infinite many solutions. But this doesn't describe the solutions. This describes the solutions, so that's what you're going to find in your book, a description of those solutions. And so another one, this is 28. 3x minus 6y equals 6. And if I graph it, so practicing my graphing, right? 0, I've been on convenient points, so we're going to get -1. And 0, we're going to get 2. And perhaps I will get another point. Let me see. What if I chose -2? I'm trying to get a whole number. Although if I didn't get a whole number, I'll just live with it, whatever. It'll be okay. And so this is -6 minus 6y equals 6. Adding 6, going to give me -6y equals 12. So -2, so that -2, 2, that worked out good. So 0, -1, 2, 0, -2, -2. If you're not this fast at graphing your lines and picking your points and doing the arithmetic, that's okay. You can pause the video and review graphing these lines, right? And so this is what we practiced all through chapter 2, and you get where you're pretty darn fast at it if you practice it. You really do. And that is something that I really notice with people, is that if you haven't practiced very much, it takes a really long time to even do just a very few problems. It's a really, you need practice in order to work at a reasonable pace. And so make sure that you're practicing so that you can work at a reasonable pace. So let's see here. If I let x be 0, then I get -2y equals 4. So I divide by -2, divide by -2. So this is -2. And I can kind of see that -2 times -2 is 4. And if I let y be 0, it's worked out pretty good, the intercepts here. X equals 4. So I'm going to pick one more point. I'm thinking about picking a y value, because then I'll put it over there and then x will be a whole number for sure. So maybe I'll pick y as 1. Perhaps. And so this is going to give me x minus 2 times 1 equals 4. X minus 2 equals 4. So when I add 2 to both sides, I get x equals plus 2, right, is 6. And I have to be careful or plot that one backwards, because I normally choose x and find y. But since I found y, and I did that because of the coefficient, and that didn't have a coefficient, so I knew that I wasn't going to have to divide and I wouldn't get a fraction. And so 0, -2 is here. 4, 0 is here. And 6, 1 is here. So remember, we're looking for the solution that they have in common. And you probably notice, well, they don't cross each other. They have to cross each other in order to have a solution in common. And so since they don't ever cross each other, and the solution is where they would cross one another, there is no solution. Your book uses the symbol no solution. It is not appropriate to use the symbol all real numbers here as the answer. And you might be thinking, but I thought we did that in chapter 1. But not every point is a solution. And so like that point is not a solution. There's only solutions on the line, right? And so not everything is a solution. And so here there's nothing that's a solution. And then just a note about always making sure that you check your work so that you can fix your error if you have one. And then you probably wouldn't take very much convincing that there's got to be better methods than the graphing method. And so it probably doesn't take very much thinking about it to realize there's some real difficulties with the graphing method. For example, what if your solution is a fraction? And certainly fractions do happen, right? And so the solution is right here, is where they cross. But what is the ordered pair right there of where they cross? Well, I mean, I know that it's under, x is under 3, right? Is it 2 and 7/8? I don't know. 2 and 3/4? I don't know. And we know the y value, -1, -2. It's not quite -2. Is it -1 and 5/8? I don't know. And so, and running a check on all of those, plugging it in and checking it to see if it's right, would be a royal pain in the tush, right? And then this one here is an example I got from my office mate, Arnie Andrazian. And a student came in and was asking me to help them in the office a couple semesters ago. So I shouldn't say probably my example. I probably should be more honest and say Arnie's honest and say Arnie's example, right? And the student had used the graphing method. That wasn't really what the student was supposed to do on the problem. That's what they weren't asked to do. But the student did get it graphed, and that would be pretty darn hard to graph that one. Actually, think about putting in, you know, x is 0, you're going to get a nasty fraction, and the same with, you know, or maybe you'll get a nasty fraction. I don't know. It just, that doesn't seem like that good it doesn't seem that good of a method to, it doesn't seem that easy to graph that one because those numbers seem pretty bad. But when he graphed it, he said to me, look, they're parallel. And I looked at it and they do look parallel, but they're not parallel. These actually cross one another way off the screen, off of the -5 to 5 screen, they cross one another. And so you have to be careful, because what if your solution is a fraction? That's hard to find. Sometimes the equations are really hard to graph by hand. And so this one is actually not that easy to graph, and neither is that one, just because it's not impossible to graph. It's just the numbers don't turn out as nice as these did. I got convenient points really easy and whole numbers really easy on all of these. But this one, if you're trying to get whole numbers, it's not going to be that easy, and I think the same on this one. And then sometimes the lines can look parallel, but they're not. And so this is an example of the lines looking parallel, but they're not. These are not parallel. There actually is a solution here. So even though you think they're parallel, they're not parallel lines. Okay. So the methods that they talked about for us is the graphing method, and you can see that the graphing method can have problems. This is an algebraic method. The substitution method and the elimination method are both algebraic methods that we're going to learn in another video, and these are algebraic, and they're like, boom, you have the solution. And sometimes people are like, well, why do I have the solution? And so the graphing method definitely gives you the why of how it would work out. And so it gives you a visual of what's going on. But the algebraic methods, they're kind of fun, though. You're going to love them. I know you are. One last comment, and then we'll be done with this video. There are 3 possibilities when you graph 2 lines. The lines are parallel with one another. They intersect with one another, and this intersection point is the one solution that you have. Or they're the same line, and there are infinitely many solutions, and this line is the solution. And so your book puts a little bit of vocabulary on that. They say when something doesn't have a solution, it's inconsistent. So this has no solution, so it's called inconsistent. These both have solution, so they're called consistent. So having a solution makes it consistent. This is called independent because the 2 lines are different, where this is dependent because the 2 lines are the same. And so you don't have to know these words, although they do say those words in some of the things and mention them or whatever have you. The main thing is that you have to know by looking at the graph when there's no solution, when there's one solution, and be able to name that solution, particularly if it meets at a whole number, and when there are infinitely many solutions, and be able to write this in the set notation that what we wrote on the other one here that had infinitely many solutions, right? We wrote it in the fancy set notation. Okay, so that's the story there, and hot diggity dog. This week's videos, 3.1 is 3.1 is done. That's what I meant to say.